Professor Drennan, thank you so much for taking the time to speak with me today. I am really excited for this conversation. I'd love to start at the very beginning. I mean, I heard that your mom actually read your entire biochemistry textbook, even though she studied anthropology. Walk me through this event and what this moment was like for you, because reading an entire textbook cover to cover is mind-blowing for me.
Yes. So my father is a medical doctor, and he used to like to say, he could understand everything I was doing, and made my mom feel kind of insecure that she couldn't really understand it. And she told me about how, if neighbors came over for dinner, they're like, "What is your daughter doing?" And my mom felt like she needed to give like a detailed explanation of this, which of course she did not need to do. And I'm
Mhm.
sure the neighbors really had no interest in the
Exactly.
details of what I was doing.
Yeah.
But then one of the structure I solved as a graduate student was in a textbook. And I thought, this is really cool to have like an image that was, my work, that we figured out what this thing looked like, and it
Yeah.
was in a textbook. So I got my mom the textbook with the idea that, when someone said, "What's your daughter doing?" She's like, "She's contributing to a textbook," and she could open up the book and like show people like, my daughter is did the work that led to this image. So
Yeah.
that's sort of what I thought this gift was going to be. And then I asked her about it, like maybe a year later or something, like, was this helping? She could open the book and point. And my mom just looked at me and she sort of shook her head, and she was just like, "It was a lot of work." I was like, "What's a lot of work? You open, you
Oh.
point, you can bookmark it, like you open it, like you could say, 'My daughter made this.'" And then she said, "But I finally finished." I was like, "Finished? What do you mean finished?" And
Wow.
that's when it was clear to me that she thought that my giving her this book meant that she needed to read the entire thing, which was absolutely not what I had in mind whatsoever. But she wanted to be part of my life. And she's like, "Okay, if that means reading a textbook to understand what my daughter's doing, I will read this textbook." And it was just, such a wonderful act of love on the part of my mom.
Wow, that's beautiful. Do you think that experience kind of changed how you thought about explaining science to people outside of your field?
I think that it helped me realize that there are a lot of people out there that really would like to understand science, that it's scary. Science seems like only smart people understand it or something. It has this kind of ethos about it.
Yeah.
But but that there are a lot of people who are curious and actually really want to understand things. And so if we can make it accessible, they will be engaged. It's not that people are like, "No, don't tell me about the science." Maybe there are some people, but there's also a huge number of people who just want to understand. They're curious, they're interested, and that if we can provide those resources to them, they're there. They're gonna read it. They're gonna participate in it. They're gonna learn it. And I always think about that whenever I go out and I'm talking to people or whatever, thinking about, how can I make this more accessible? Is this something, can I get like at least 90% of my audience really appreciating what I'm doing and understanding it, feel like, "Oh, I got it. I was part of that adventure, that discovery." And if I can get that buy-in, that just makes me so happy.
Definitely, yeah. I absolutely agree with you. I think there's a huge stigma around science being only for smart people. And
Yeah.
I think that really makes this gap between scientists and normal people. And what's so ironic about the situation is that science is for everybody. At the end of the
Yeah.
day, science is trying to help everybody. We need to make science more accessible to students, to people who might not be as intelligent as scientists. Moving gears a little bit, your mom pointed you towards ribonucleotide reductase, which ended up
Yeah.
becoming such a central part of your work. For someone hearing about it for the first time, what exactly does that enzyme do and why is it so important?
Yeah. So this enzyme converts the building blocks of RNA. to the building blocks of DNA. And of course, DNA is our genetic material,
Right.
and that makes, the codes for all of our proteins and everything in life. And there are diseases if there's mutations in our DNA that causes problems. So the, it's the RNA also is involved in making proteins, and so these are just essential building blocks in the cell. So this particular enzyme we study does this conversion, and if you inhibit it, and there are different chemotherapeutic drugs that are used to treat cancers that inhibit this enzyme, and that stops, if you can't make the building blocks of DNA, you can't make more DNA, so you can't have cell divisions, you can't have the spread of cancer. So
Right.
it's of fundamental importance in the cell, and I think there's thinking about it more in terms of treatments of different cancer. And cancer is just like, such a beast. It's like there are all these different kinds of cancers. And very recently, actually, Eli Lilly reported, I think it was Eli Lilly. Was it Johnson Johnson? Oh no, I better get that straight. Now I forget who it was. Don't quote me on it. But
I will.
some group figured out that there's a particular inhibitor of the enzyme I study, and we're actually currently studying the mechanism of it, which hasn't been fully
Wow.
understood, like how it actually inhibits. But if you for bladder cancer, if you deliver it in a different mechanism, so in the way that I think a lot of chemotherapeutic drugs are delivered, or IEVs and other things. And they figured out that the way that you deliver the drug makes a huge difference in terms of treating bladder cancer. So it's like really interesting enzyme to think about. Maybe it's good for treating one kind of cancer, less good for another, but maybe the way you deliver it, or in combination therapies with other things. And so it's a really important target. I'm also interested in it in terms of a potential for antibiotics. And
Mm.
normally you stay away from things that, like, if you inhibit the human enzyme, that's like a cancer drug, because you
Mhm.
don't want to treat a bacterial infection that,
Right.
kills this enzyme and causes
Yeah.
damage to your cells. But the more we study these enzymes, we realize that they're extremely different from each other, the human version and the bacterial versions, and that there are ways to actually inhibit bacterial enzymes that have no effect at all on the human version. And so that's one thing that my lab is really interested in doing, is understanding these enzymes from different species and figuring out ways that we could be maybe very selective, and not even just an antibiotic that could kill lots of different bugs, but even more specific, like just going after some of the pathogens that drug may not affect the commensal bacteria, which we need in our gut to be healthy. So these enzymes have really specialized over time for their particular environment, and we can use that specialization to just target specific organisms. So I'm really excited about that.
Yeah, that sounds so fascinating. So behind all these enzymes, there's a particular mechanism, right? So I've heard that R&R uses a radical mechanism, which
Mhm.
is pretty unusual. What makes that different from typical enzyme reactions?
Yeah, I mean, there are a number of enzymes that will use sort of radical based chemistry, but it is, I like thinking about it in terms of the Avengers, when you would call the Avengers to come versus maybe calling the local police. If aliens are invading New York City, then you want the Avengers. But if, someone's purse was snatched and you have the Avengers, they're probably going to destroy like multiple city blocks while they try to
Yeah.
fix the situation. And so, like, radical based chemistry is like that. If it's really hard reaction, that's the only way you can do it. Yes, then you figure out how to safeguard it. But if you can do the chemistry in a less dangerous way, that is absolutely what you're going to do. So
Right.
it's sort of only employed when there isn't really another good option, but then there's all these layers around it to make sure that nothing gets away, that it's safe, that it doesn't kill the enzyme, it doesn't kill your cell. And that's part of what fascinates me, is how do you design this enzyme, something, a biological molecule, a protein molecule, to do really difficult chemical reaction using radicals, which shouldn't really, if we think of the free radicals, you can't control them,
Right.
but you
Yeah.
can. Somehow it's designed to control that and not allow bad things to happen. And I want to understand what those design principles are that allow for nature to use this really dangerous chemistry safely in our bodies.
Right. Yeah. I think going off about R&R's unusual nature, I also learned that this enzyme works with multiple substrates instead of just
Yeah.
one, which
Mhm.
sounds a lot more complex than typical enzymes. So
Yep.
when in your lab, what makes studying it especially challenging?
Yes, I think there's a number of things that make it challenging, and that is definitely one of them, that it has all of these, it can act on all of these different substrates, and that's regulated. And so when you're thinking about studying it outside the cell, you're usually like pick one substrate and look at that being turned over. But if you really want to relate what you're learning to the cell, you have to think about what are the actual amounts of these things in the cell under different conditions. How are they competing with each other? How is the enzyme kind of not getting inhibited by the wrong kind of substrate at that time, and it's supposed to do the right substrate? And it's just trying to think about the relevance of what we're doing in the cell is one thing. And then designing the right kind of assay. Like we now have an assay where we can have all the substrates there together and sort of look at what's happening in a more sort of cellular context. Um, and then to have active enzyme, we have to reconstitute the protein with the radical species. And we usually don't get like a really good amount of active enzyme. And so we're always worried about that as well, that we're sort of, that the protein we're studying, in the cell, I think it is more active than what we get. We don't really, we're sort of missing something, that we don't get it fully active when we're studying it. Um, and and then the other factor is that I think to do all these levels of control, the enzyme has all of these conformational states, which is great for us to investigate with the
Right.
tools we are looking at these. But it's also very complicated because it's doing many things at once, and we're trying to figure out how to slow everything down. It's like, okay, I want to see this part, but this is happening at the same time as this.
Exactly.
And then, yeah, so it's yeah, it's kind of like, trying to understand how, a person is able to juggle multiple things at the same time. And if you have your eye on one of the balls going around, you're missing what's happening with the other ball that's going around, because you're watching
Right.
this one when this one's happening. and
Mm-hmm.
and then if we kind of slow everything down, it's like, okay, let's give it one ball and we'll study that, but that's not really mimicking what's happening in the cell. So
Right.
it poses many challenges, but that's why it's interesting, and that's why I'm just like, I am going to understand you. I'm gonna you are not gonna get away with it. I saw you. What did you do? You just dropped one of the balls. Okay, we're yeah, watching
Right,
you.
yeah. So there's multiple substrates. So do these substrates bind to multiple active sites, and then do those active sites lead to different conformational change? Like does each active site or does each substrate have its own purpose in the particular enzyme?
Yeah, I mean, we don't really fully know the answer to that. I think, and it depends on which particular ribonucleotide reductase you're looking at in the different
Mm.
classes. I think for the one that's found in humans, it loads up with the same substrate in both active sites, and then kind of does a round of turnover, one then the other, and
Oh,
then it
okay.
resets. But we don't really know that for sure. It's
Mhm.
possible that it could load up with two different substrates at the same time, but then it's still just doing one active site at a time.
Okay.
Um, yeah, in some of the forms, we think that it may be more complicated, that you each active, when it has two active sites and it's a dimer, they mo they they may be interacting with different substrates. Um, Yeah, there's still a lot of interesting questions that we don't know the answer to.
Yeah, I think that just ties to the complexity of its nature, really. So, what's something that about R&R that scientists still don't fully understand?
Mm. Uh, I there are a lot of things. I think for the best studied member of the family is the enzyme from E. coli. It's a class 1A from E. coli. That's was the first one discovered in the 1960s and had the first structure solved in the early 1990s. And we're still it's kind of my lab's model system because a lot of the data is on this. And so we really want to have a full story of how this one works. And then the next challenge is like, do any other ones work like this? Maybe, maybe we need another 40 years on the next one or whatever. But it's for the best studied one where we know the most and we've learned a huge amount on this one.
Mhm.
One of the key unanswered questions is that there has to be every time you turn over your substrate, you form there are two cysteines in the active site that form a disulfide bond, and you need to re-reduce them to do the next round of catalysis, go from this disulfide bond, break it, and then have these two cysteines with these SH groups instead. And really, no one knows how that happens, how there have to be all these conformational changes to do this to do this re-reduction reaction. And that's like a big unanswered question of how this happens. Same thing needs to happen for humans. We don't understand that part of the reaction at all. So that's kind of one of the key missing ingredients is this kind of we can understand kind of going from the beginning of a turnover to the end, but how you reset the enzyme for the next round of turnover is still a great mystery. So that's kind of the biggest hole, but there are many other ones where it seems like that if you make too many of the deoxyribonucleotides, if it's too active, it's turned off
Mhm.
by the binding of a deoxyribonucleotide to the enzyme. It turns it off. And we understand the mechanism by which that happens now. Think there's still a few unanswered questions for humans, but we have theory. For E.
Yeah.
coli, we understand it really well. I think it's going to be the same in the organism that causes gonorrhea, the sexually
Mhm.
transmitted
Right.
disease. That's really similar to E. coli.
Interesting.
And kind of know, we really don't understand it in anybody else. So there's, every organism has at least one ribonucleotide reductase. Many have three. They have plan A, plan B, and plan C, because if you don't have an active enzyme, you're dead. So they have
Right.
multiple flavors of these enzymes. And so what we know so far, it seems like there are multiple different mechanisms for how that works. And those sites that turn off the enzyme are really key sites for inhibitor design. So we kind of need to understand it in lots of species. So that's also a
Mhm.
big kind of unanswered area. So um, there is a lot more work to do, actually. And I feel like a lot of times when we finally get one result, it raises more questions than it answers. So in doing the work, we're constantly being surprised. And
Right.
that means that we're not done yet.
Right. No, that makes sense. I have a question actually. So you were mentioning the conformational changes in relation to the disulfide bond. Do you
Yeah.
think that that could be tied to like some kind of complex condensation reaction that's taking place?
Um, yeah, so the general idea that we have so far, or I guess the pieces that we know, is that originally um, the reducing equivalents come from NADPH, which is a common source of reducing equivalents in cells, um, through thyrodoxin reductase and thyrodoxin, which are common also in terms of providing reducing equivalents. So thyrodoxin will interact with the enzyme. With the C terminal part of the enzyme, and then that somehow moves into the active site. And how those different binding arrangements and kind of what causes the large conformational change and exactly how it happens. We don't know are if there are, if thyrodoxin has a stable binding site or not, or what is the oligomeric state of the rest of the protein when all of this is happening. um, yeah, there's no real evidence of sort of bioconjugates in the system that I'm aware
Mhm.
of, but um, yeah, it's sometimes there's been many things we were unaware of in the system until all of a sudden some experiment was like, hey, this is happening.
I think,
And
yeah.
so I don't want to ever rule anything out. I feel like you need to keep an open mind because this enzyme is constantly surprising one.
Definitely. I think that's really important, especially in the field of science. Switching gears just a little bit, looking back, what originally drew you to biochemistry? Was there like a specific moment or experience that made you think like, yes, this is what I want to do?
um I I don't think there was anything really specific. I think that it kind of took me a while to what I've been interested in is kind of always what I was interested in. Like I think my interest didn't really change, but my ability to kind of articulate what I was interested in or recognize that that is what I wanted to do. Um, I I was always fascinated with kind of how things worked and just curious about the world in general. And so I like, biology was just kind of, how are cells alive? Like, how does that work? Like, just, it was just fascinating to me. It just didn't seem possible that
Yeah,
a human could
exactly.
exist.
Yeah.
And it just was really, really fascinating to me. And then when I was in high school, I took chemistry and I had a teacher who was just made the subject deadly dull. And I was in chorus, and I used to try to plan all of my music lessons to interfere with chemistry so I wouldn't have to
Oh
go.
my gosh.
Um, until he tried to figure it out. He goes, "Thought that, yes, you get out of class for these music lessons, but isn't it supposed to alternate between the different classes? It seems like you always go during chemistry." And I was like, oh,
Oh my
do
goodness.
I?
What a
Oh,
cool.
hadn't noticed that.
Oh my
Um,
God.
yeah. So then I got to college, and I was still interested in biology. And they're like, well, if you were going to be a biology major, you need to take chemistry. And so we recommend that you do the chemistry before you go on to the other biology classes. And I was like, no, I don't need to take chemistry. No, don't make me
Oh my
take
God.
chemistry. And so they insisted, and so I did, and I loved it. I just absolutely loved it. And then I was like, okay, I only want to do chemistry, but I still am really want to understand like how life works. And so, and I was like learning about all these cool chemical reactions, and I just realized that like the things I was fascinated with are just like the hardest reactions that are necessary for life. And so those are radical reactions. So
Yeah.
I got there in a very weird way by first being in love with just understanding biology and living things and how that
Right.
works.
Yeah.
And then kind of bringing it back to like, well, if you're going to understand that, I feel like to have true understanding of something about in biology is at the sort of molecular level.
Mm.
And so I would like, okay, so this happens because of this pathway, which really requires this enzyme, which requires this enzyme mechanism. And then I'm like, but how does that mechanism work? And so I just kept going like deeper and deeper every time he was like deeper and deeper. And then I'm like, okay, I need to know what the enzyme looks like if I'm going to understand how it
Mm.
works. And so that took me to structural biology. So I just kept asking why, basically. I was interested, and then it's like, well, why does that work? And how does that work? And why does that work? And how does that work? And that then got me to where I am. But I really dislike chemistry, and I swore I would never take it again, and said, how much I disliked it. And so I tell everybody now, like, never say that. If you dislike a class, never say, I'm never going to study that again. I don't like it, because you might become a professor of that subject
Oh
and
my
do it for the
God.
rest of your life if you say that. The fact that I'm a chemistry professor
I
now is just
know.
like high school me would have
Oh
been like,
my
what
gosh.
are you doing?
As a professor at MIT, you're not only doing these kinds of research, but you're also mentoring students. So, what do
Mhm.
you think has been the most rewarding part of teaching?
Well, it definitely is the students, and just watching people come in and both with undergrads and graduate students and sort of in their first year. And they're like, how did I get into MIT? Or at least a lot of them are,
Uh-huh.
and feeling really insecure about whether they should be there. And then watching them realize that they are really good at this and they do belong there. It's just so rewarding seeing people take ownership of the research they're doing, or ownership of their lives and what they're going to do after they finish undergrad. Um, and a lot of students, both undergrad people who are in my classes or undergrad advisees, and graduate students, stay in touch. And they just reach out and let me know the sort of new things they're doing or new challenges. And um, yeah, and sometimes I hear from people that I didn't even really know all that well, but somehow just me being, sort of a different kind of professor in some ways that seem more approachable or something, that they just saw me, and it's like, okay, I don't know, I don't see myself as like, a sort of more average scientist or whatever.
No,
And
no,
they
no.
just like,
It's
I
your
just don't see myself
personality.
as that. But then they look at me and it's like, well, I could be more like Kathy or something. Like that's like,
It's definitely
uh,
your personality.
yeah. And that just makes me really happy, because I feel like it's when great science really gets done, it's by a whole lot of different people with different ways of thinking about things and putting things together. And if we just keep selecting for people who are sort of identical, we're not going to have the best science being done. And so
Mhm.
if anybody kind of got to know me and that motivated them to go into science or stay in science, that just makes me very happy.
That's beautiful. What do you notice about students who really succeed in science? I mean, like, what kind of mindset do they have?
I think it just, resilience is so important, that, if you're really going to be doing research, not everything is going to work. Most of it won't work. And that you just get back and keep trying. And that just, kind of stubbornness and resilience kind of combined. And I think, being brave enough to say, okay, my research is requiring me to learn something new. And
Mhm.
so, yeah, I'll probably fail, but I'm going to try it anyway. And just going with not really feeling like this is likely to work, but you just keep getting up and doing it again, and it will eventually work, and you will be learning things while doing that. But the just that kind of determination, which often comes out of curiosity, and it's just like, I must understand this thing that I'm working on. Like, there is no other alternative. I must understand it. And
Yeah.
that kind of motivation and drive just gets you there. And if you don't really, or if you're not that passionate about what it is that you're doing, or you just let fear get the best of you, like, and kind of self-select yourself out of that challenge. So yeah, it's just that ability to kind of be resilient, which sometimes is just about finding your support network and having other people who, on day there's always days where we all want to quit, and have those people who are like, nope, you're not quitting today. And are just there to kind of help pick you up and dust you off and send you back, to do it another day. So Um,
I think we
all
definitely need
yeah,
more people like that in our lives to keep
yeah.
pushing us.
Yeah, everyone needs to find their village of people who will just support them in what they're doing. And I think that can be really challenging because people outside of science sometimes were like, well, if it's that hard, why don't you just quit? And that's not, it's just, it's like, yeah. So having people who get that what you're doing is sort of, they're just going to be there cheering you on for the journey.
Mhm.
And yeah, it's finding that is really important, or building that. And for some people it's parents who are just always supportive of them, and for some people they don't have that, and so they need to find uh, people who will be just supporting them in what they're doing. And it can be a friend group, a peer group, it can be a mentor, a teacher, it can be all sorts of different people. Grandparents, sometimes I hear like the parents are just like, can't you do something more sensible? But there's a grandparent, it's like, go do this thing, you can do it, um,
Absolutely,
whoever,
yeah.
yeah. Whoever that person is, just let them be there for you, and that's a big part of it.
Yeah, a lot of high school students watching this are interested in science and always don't know where to start. What is one piece of advice that you would give them?
Well, I think the biggest thing is that if you want to do it, you can do it. I think getting back to this myth that you have to somehow be absolutely brilliant or you can't succeed as a scientist. If you want it, that's it. That's like, you want to do it. You're passionate about doing it. That is the thing. And when you really focus on a problem and it's your research problem that you're doing, you're the person who knows it best. You know, expertise is about just reading and doing and reading and doing, and you can make that happen for yourself. You don't have, no one's born the expert. And so if you want it enough, that can be yours. So don't self-select yourself out thinking maybe I'm not smart enough, maybe there was something I was not born with that means that I can't do this. You don't have to be born with anything, you just have to want it, and then you can do it.
Yeah, that's beautiful. All right, Professor Drennan, we're down to our final few minutes, so I'm going to ask you a quick rapid round. You
Hmm.
can have one sentence or one word answers even.
Hmm.
So, what is one word you'd use to describe enzyme research?
Fun.
Okay, beautiful. What is the most surprising thing you've learned about R&R?
um that it is like a Rube Goldberg machine, which are these things that sometimes you build in seventh grade, where you have like blocks set up and like you knock one, then it knocks the other ones, that
Oh,
then
yeah, yeah,
causes a
yeah.
ball
I know
to
what you're talking
roll
about.
off the table. Yes, that's how the enzyme works, that the act
Mhm.
of doing one part of the reaction causes the next part of the reaction to happen.
Amazing. Okay. What keeps you curious after so many years in science?
I think just I my my mom reading that textbook and telling me to work on
Aww, that's
days.
beautiful.
It
Yeah.
just she picked for me such an amazingly cool thing that it makes me wake up being curious every day. So it's
Aww,
the system, my system my mom picked for me,
that's
that is the
beautiful.
magic.
Oh, yeah. What is one habit that made your moment in life successful?
A habit. Um, I I don't know. There's all sorts of things. Okay, I'll be fast. I'll just think of one
No,
thing.
it's okay. Take
Um,
your time.
so I think one thing that has been very key for me is being a dog owner. So I I think a lot of my big breakthroughs, I was like really frustrated with what I was thinking about, and I was
Right.
stuck. And I just got out of my head and went for a walk with my dog. And often I would have these like, oh, wait a minute. You know, how
Those
this
like
is
light bulb
happening.
moments. Yeah,
Light bulb moment. And it's when you remove yourself from that situation and you
Mhm.
kind of stop thinking about it. And often,
Absolutely.
like going out in nature and
Yes.
just
Yeah.
and exercising and things was key. So I
Yeah.
started, I think part of the habit of success is just if you really stuck, I take my dog for a walk.
Wow, that's amazing. Okay, last question. What advice would you give to your younger self?
Oh, be kind to yourself. I it took I'm still not very good at it. And that I'm too hard on myself, too critical that I don't do things well enough, or I could have done it faster, I could have done it better, or
Wow.
I
Oh my
missed
gosh.
doing something. And I would just go back and tell myself, just, give yourself a little more grace.
Professor Drennan, thank you so much for sharing your journey and your insights today. This was so incredibly inspiring, and I know so many students, including myself, have learned so much from this and will take a lot away from this conversation. I hope we can talk again soon in the future. Thank you so much for your time.
Thank you very much.